Good morning, good afternoon, and good evening. Thank you so much for joining us. My name is Haley Thomas, and I'll be your moderator today. Today's presentation, entitled How to Deal with Performance Issues in Parallel and Series Pump Operations, will be presented by Mr. Stu Watson. Stu is an instructor and consultant for John M. Campbell and Company and has over 15 years experience in the oil and gas processing industry. His specialties include piping and rotating equipment, as well as process startup and engineering design. We're so glad you could be with us today, Stu. The floor is now yours.
Hey, thanks, Haley. Good afternoon or good morning, ladies and gents, wherever you're tuning in from. Thanks for joining us here. I hope that some of the concepts that are presented in this brief webinar are useful in your work. I found that a number of the participants attending the ME44 course, which is Fundamentals, Pumps and Compressors, frequently identify key learning points surrounding performance expectations, where we have a pumping network that may involve looped lines or parallel and series pumps. And so, as an instructor, I was a little surprised. We put this brief webinar together using some of the materials from the ME44 materials to highlight and review this subject. So I hope it connects to your work and is meaningful. So today we're going to be talking about some of the basic theory surrounding system and pump curves, and then apply that theory to pumps that are installed in parallel and series. We'll also consider typical applications for parallel and series pumps, and then we'll look at the effect on performance factors such as net positive suction head, power, vibration. And then when we close out today, we will look at some of the areas of concerns, almost like a checklist of action items to just double check your system. I will also note at this point that through most of these discussions today, we talk about centrifugal or dynamic styles of pumps. If you're working with positive displacement pumps, there are some differences in the analysis approach that's used, so just keeping that up front. Okay, so when we talk about system curves, and I know that this is probably straightforward for a lot of people, that they're like, yep, we know what a system curve is, but when we talk about a system curve, think of it as a representation of the energy requirements to induce a specific flow through the pumping network. So if we were to look at Bernoulli equation, Bernoulli is simply an energy balance between different kinds of energy, potential, kinetic, and so on. So how the system utilizes or demands energy is represented on this system curve. So it really represents your network, and getting a strong understanding of that is very important. The second part in the equation is the pump curve, representing the capabilities of a specific pump, running at a certain speed, a certain impeller size. And in an ideal world, this would be a horizontal line. But because of friction internal to the pump, then we see it sort of sloping downwards. And I'm sure that we'll see that as we move into the next slides here. So going through the major components of the system curve here, we have our axes with, on the bottom axis, we've got flow rate in gallons per minute or meters cubed per hour if you're in the SI world. And we talk about energy on the vertical axis. Well, we don't talk about energy so much, we talk more about head, and we represent that energy in units of feet or meters. You can calculate head from your pressure, or differential pressure across your pump, which would bring it proportionate to specific gravity, but we utilize head on this chart because that means that a single pump curve would be independent of changes in specific gravity, which is very useful for us. So when we talk about a system, we can break the loads up in the system into two categories. The first being static components. These would be changes in elevation or differential pressure across the pump, pumping from one tank to a higher pressure tank, or from a low level to a higher level, up a hill or a mountainside, if you like. And then the second component, which we've added right on top of here, we call the dynamic head. So this would be a function of friction, whether that's calculated due to friction loss in pipelines by a Darcy or a Colebrook-White equation, or whether that's a function of perhaps you've got a reinjection program and the number of reservoirs and that reservoir nature will drive that dynamic head. When we add those two together, we get what we refer to as the total system curve. And typically, here's our pump curve. We see that downward curving nature that we're familiar with. Our operating point is the intersection of these two curves, giving rise to a specific head and flow rate where those two curves coincide. We should also note that in reality, definition of terms, when we make these calculations, there are some variation in that the static head pressures in vessels may change, or the elevations between levels in two tanks may change. And so there could be variation in your static head. And similarly, in your dynamic head, there could be changes in the dynamic head as a result of an adjustment to a control valve, or a change in a reservoir reinjection program. If I put more wells on or take wells off, I'm going to change both my static and my dynamic head. So what I urge people to consider is a system operating envelope instead of just a singular system curve. And here you can see that that infers that we would operate over a range of conditions. And obviously that means different loads on our pump. This chart shows a vendor's typical pump curve. The chart illustrates performance not just for a single impeller, but for multiple different sizes of impellers, as you can see over here. The chart also illustrates the efficiency, operating efficiencies, and you can see those efficiencies radiating outwards from a point known as the best efficiency point here in the center. Over on the right-hand side here, you can also see lines of constant hydraulic horsepower. So this would be horsepower ratings that would be transferred back onto the driver. These are this curve is very useful for us in the troubleshooting process, of course. The top curve at the top here refers to net positive suction head requirements for that pump, which is something that we need to be very cognizant of to prevent damage to the pump. Now, if we were to place onto here our system curve, we've been very fortunate here that the system curve passes directly through the best efficiency point, which is often not the case, but where the system curve and our pump curve meet is our operating point. And so we can see if we change our impeller sizes, that will have different operating points, different flow rates based on the different impeller sizes. We get a similar effect if we reduce the speed of the pump. Here we're just changing the size of the impeller. If we now place our operating envelope, where we could see that may occur from different operating conditions that may change our system curve, now we would actually have a range, or one impeller would have a range of operating flow rates that we would be operating between. The other interesting factor here is that you can see that the pump horsepower is increasing to the right. So as we move from our initial operating point to our second operating point, we can see the pump horsepower is increasing from 15 to about 17 or 18 horsepower. Also looking at the net positive suction head, we see the net positive suction head at around about 6 feet of net positive suction head. And as we move to our other point, we see the net positive suction head increasing to about 12 feet of suction head. So this can be a real problem if you don't have enough net positive suction head available. And here's that discussion on power that I mentioned a second ago. So talking more about series and parallel pumps now, trying to understand why we have them is important. And some of the various reasons that we may consider having pumps in series and parallel: operating flexibility, allowing an operator to have multiple units installed in parallel where they can take a unit offline to be able to do maintenance and so forth, or perhaps they've got different performance requirements in a pipeline and they can put more pumps on to be able to move more or less fluid, turn down or increase production. And we may have an existing system where we add pumps to try and increase capacity, and this is frequently where we see problems starting to crawl in, so this is where we need to be the most cognizant of issues. There may be specific process requirements where we need to operate at multiple different pressures, and so we have to pump between those pressures. Or frequently where I've seen parallel series pumps is in where we have NPSH problems, and we require booster pumps to support a pump that requires a high net positive suction head requirement. And so we would need a booster pump to provide adequate net positive suction head available. This is one of those instances where the fluid, which in this case is a raw NGL, is flowing out of that tank and into the suction booster pump. It passes then on to a vapor separator to break out any entrained vapors, and then you see our high pressure delivery pump. And in this case, the high pressure delivery pump is a reciprocating style pump, reciprocating plunger style pump, which is prone to having very high net positive suction head requirements. And this configuration, I believe they had inadequate net positive suction head available in the original design, had to add that suction booster pump in there. And this is quite common in the industry to see this sort of design. So looking at pumps in series, what I've done here is I've drawn onto this chart from that vendor pump curve that we had previously. I've drawn the pump curve for a single pump. Then as we look at two pumps with identical impellers in series, then the heads for those pumps are added vertically. So at any one flow rate, you can see here at 0 GPM, you can see two pumps would generate 400 feet. If we look over here at about 220 GPM, we can see that we end up with about 300 feet of head. So it's key to note that the heads here are added vertically. The challenge in this process is that the pump curve now drops fairly steeply. This new pump curve drops steeply, which means that as your system curve increases on here, you have a sudden drop in performance. Let me illustrate that by drawing onto here the system curve. So here's our system curve that we'd considered previously, and we expected our operation at about 200 GPM. Now when we increase capacity, we run two pumps in series, we see an increase in capacity to around about 280 GPM. That's about a 40% increase in capacity for running two pumps. So now, if we consider what's happening to the head, we see the pump head here increasing from about 160 feet of head to around about 250 feet of head. So that means that each pump at this point is only moving about 125 feet of head. Let's look at this on the pump curve to get a bit better flavor. So drawing onto here my system curve, there's my operating point for one pump. Right, and then if you remember, our flow rate actually came up at about 280 GPM. So that means that each pump is going to move 280 GPM. So you can see the operating point when we move to 280 GPM, we see the pump head drop right down. So the pump head is now reduced from 160 down to around about 125. Oops. So one thing that we need to note here is that we have moved a long way to the right of the pump vendor's curve. And this can introduce a lot of other problems. We've not only increased the horsepower on the pump, on each pump, we have also reduced the operating efficiency And when we move this far to the right of the vendor's pump curve, we start to put a lot of additional load on bearings, increases in vibration. We see potential damage for seals, that kind of thing. So this operating point here I'd be very concerned about, and I'd be definitely going back to my pump vendor and verifying with him, how is my operation of my pump? Is it still adequate right here? Now when we consider pumps in parallel, the approach is a little bit different. But again, we're considering two identical pumps in parallel. Again, here we've drawn the pump curve for that same pump impeller onto this chart. The unit axes on the are a little bit different, so the curve looks a little different here. But it's the same pump curve drawn on this chart. And then we're adding flow rates horizontally here. So you can see from this point here, we're about 220 GPM. And as we push out here, we're at 440 GPM. So this dotted line refers to the performance of both pumps operating in parallel. The problem that you get into here with pumps in parallel is that this now new combined pump curve is much flatter, and as a result, the changes in head make a rapid change to the pump performance, pump flow rate. So drawing onto here my pump curve, you can see that the increase in capacity is going to be a direct function of the system curve. My system original pump with one pump running 200 GPM, now with two pumps running I get about 230 GPM. So that, in this case, that's about a 15% capacity increase. If I had a different shape system curve, then that's going to have a very different increase in capacity. So it's very important that we understand this effect. And quite often this is overlooked. People think that, oh, if I start another pump, I'm just going to move twice as much flow rate. And unless there is a strong understanding of the system curve, can that actually be determined? And now we need to pass that information on to the actual pump curve, which is a very important part in this process of understanding what's happening. So drawing on my system curve, I can see my operating point for just the one pump. And now I need to start to understand what happens when I increase and add a second pump to the operation. So the first thing that we need to do is draw onto here the operating point that we saw was about 230 GPM. And that coincides with an operating head of about 185 feet. So what's happening here is the pump performance, when we move from one pump, when we start that second pump, in order to increase the capacity up the system curve, the head increases. That means that for each pump, we actually back up the pump curve, we back up the pump curve to this point here. And this becomes the operating point for each pump. And you can see at this point that it is the total head but half the flow rate, which is what we'd expect. So this is why it's so important to have a strong understanding of what the system curve looks like, because you can determine just how much increase in head for that second pump running that you need. Very important. So the other thing that's important to note here is we see that the pump horsepower now has actually decreased. So we've dropped the pump horsepower from about 15 horsepower down to about 12 horsepower. And we've also reduced the net positive suction head. So the net positive suction head was up here around about 6 feet of net positive suction head requirements, and now it's reduced almost down to the minimum 3.5 feet, something like that. Okay. So some things for you to be thinking about with your pumps as you see pumps being installed in parallel or series. My first comment is to verify your actual performance. What is the actual head and capacity versus what you'd expect? When you turn that second pump on, we have a preconceived idea as to what the increase in capacity is going to be. And I urge you to go and run the calculations, run them through the pump curves. As you can see, it's pretty straightforward, and determine actual conditions. The biggest challenge that you're going to have is establishing your system curve. And that system curve may be something that you develop through either calculation or field testing. So there's different ways to determine your system curve and find out a good way to plot that onto your pump curve. Always consider variations in your system curve. Thinking that life is static and doesn't change is a little falsity, and trying to understand the effect of control valves or changes in reservoir, injection reservoirs is very important. Then verify your actual operating efficiency and proximity to best efficiency point so that you can determine horsepowers and establish what your driver capability is. You could see that as we moved into that series pump configuration, that we actually could have overpowered one of our pumps and resulted in driver damage or potential damage to electrical switchgear. Then I urge you to also look at net positive suction head. Make sure that your net positive suction head available is always greater than net positive suction head required with a safety margin involved. Use a minimum 3% safety margin. Your vendor can also give you guidance on your safety margin that you need there. And you can see that you need to consider that not just for the single pump configuration, but for 2 pumps running. If you've got 2 pumps in series, you'll see your net positive suction head requirements increase dramatically. You also want to verify your operating point. As you start to move further and further away from the operating point, then minimum flow conditions on the left-hand side of the chart, or concern towards vibration and bearing loads and seal damage, if you're seeing those things, you might want to go back, look at your operating point on the pump curve, and then talk to your pump vendor about the suitability of that operating point. It's also important to look at configurations where you have different pumps. So we have simplified the analysis here, no doubt, and used 2 identical pumps. And I'm sure there's many of you out there running pumps with different size impellers or different makes even, and trying to bring those charts together becomes more and more complex. There's different ways of doing that, and I've built spreadsheets in Excel, replotted pump curves, that kind of thing, in order to make that analysis, but it definitely gets a bit more complex. Work closely with my guidance there would be to work closely with your pump vendor in that analysis. And then finally, do consider all operating combinations. It's easy to overlook some of the key or fundamental operating modes that may be problematic. So it's at this point that I open the floor up for questions. I hope this has been meaningful stuff and connects to your all.
All right. Well, thank you, Stu, for sharing your expertise with us today. Like you said, we're going to move right into the question and answer section. We've had several questions that were submitted by our audience members. First off, let's start with John from Alaska. John asked, how would you go about analyzing a system that contains different pumps?
Hi, John. Thanks for tuning in, man. Great question, and absolutely, this material has simplified that issue immensely, and a lot of people are going to be trying to do this analysis with different size pumps. The first thing that I do in this process is I get a hold of the 2 different pump curves, and I look at all my operating considerations and usually plot my system curve onto each pump curve to make sure that operation under each pump is not going to get me to a problem. So I will plot if one pump was running, how does that look for each pump? The next thing I need to do is look at the operation with the pumps combined. So there's a couple of different ways to do this, and the way I've done it in the past is to either start to plot the second pump onto the first pump curve, or generate a curve in Excel and plot the 2 pump curves one on top of the other in Excel, and then I can drop my system curve onto that. Once I know my new operating flow rate, then I can plot that new flow rate back onto the original pump curves and establish operating conditions such as horsepower, net positive suction head requirements, operating efficiency, etc. So that's the approach that I would urge. And as I said before, always reflecting those points back to my vendor. Great question, John. And it's definitely it's with this process that we need to be cognizant of all the different operating conditions. Thank you.
All right. Next, we have a question from Russell from Edmonton, Canada. Russell asks, is there a difference between the hydraulic power equation and the power represented on the vendor's pump curve?
Great question, Russell. The power curves or the power lines that you see on the pump curve, as I mentioned, were lines from the vendor which are based around using usually cold water, unless it's mentioned otherwise on the pump curve. So the vendor should be giving guidance on that specific pump curve as to what those curves are for. There is a way for you, so this is the pump curve, and here's my system curve on here. And there is obviously the hydraulic power calculations that you're inferring to, and you have those calculations, those equations right there. And if we were to plug into these equations values of 1 for specific gravity, and then utilize the actual efficiencies that you're getting off the curve here, so at the best efficiency point of 55, plug that into that chart, we should be getting the 15 horsepower. So that you can use these equations instead of using these lines. I guess that's the key learning here.
Okay, great. And we have time for just a few more. Sarah from Houston, Texas wants to know, does API 610 give any guidance on vibration limits or how to determine the allowable operating range?
Sarah, that's a great question. To answer your question, and if I can read into a little bit, how far can you extend beyond the right-hand side of these curves? How close to the vertical axis can you operate? What is the operating map that you can utilize for your pump? What's that defined by? And vibration is a big problem in this process. As you get further and further away from the best efficiency point, then vibration will increase. There's also the consideration of minimum flow, and over on the vertical axis we see minimum flow. So if API does give some guidance, API 610 does give you some guidance, and this is an extract from page 43 where they talk about vibration limits as a function of best efficiency point. And so at the best efficiency point here, you can see the vibration limits are at their minimum. And they've actually drawn what they call a vibration curve on here, vibration flow rate curve. And the vendor offers two vibration limits, an allowable and a maximum, giving rise to an allowable operating range and a maximum operating range. And API 610 gives some guidance in here in terms of what those allowable and maximum vibration limits are. So in some sense, they infer some operating range, but to be honest, you need to be working very closely with your pump vendor here, asking him questions such as, what would be my expected vibration at this operating point, so that you can compare what the pump vendor is predicting with what you're seeing in the field. I hope that answers your question.
All right. Thanks, Stu. That now concludes the question and answer section of our webinar.
Thanks,
Yeah, sorry. Unfortunately, we didn't have enough time to get to everybody's questions, and we would like to apologize for that. If anybody has any additional questions, you can feel free to send them to webinar@jmcampbell.com.
Great.
And I want to say thank you to everybody for joining us. If you have any ideas about future webinars or any comments, please let me know at the number on the screen or at webinar@jmcampbell.com. We look forward to seeing you in an upcoming John M. Campbell & Company course. And thanks again, Stu.
No, thank you. Thanks so much, guys. Thanks for tuning in.